WG64 is dying. But what for? The gigantic star's approaching farewell from the cosmic stage is, for us, a spectacular research subject. After all, the stellar colossus is considered a hot candidate for the next supernova to be observed from Earth. But what dramatic changes indicate that the universe will soon be poor by one of its largest known stars? How did the experts manage to create a breathtaking close-up of the celestial body, although it's about 160,000 light-years away from us? And above all, when exactly will WHG64 explode? In our everyday perception, the sun often embodies the ultimate in the cosmos. No wonder, since our central star has a staggering diameter of almost 1.4 million kilometers, and alone contains 99.86% of the total mass of the solar system. Although our Earth would fit into the sun 109 times in diameter and as much as 1.3 million times in volume, we must not forget that there are much larger giants out there that would make even our mighty mother star look like a puny pinhead. One of them goes by the name WG64, located around 160,000 light-years away from us in the Large Magellanic Cloud. This red hypergiant is estimated to have 16 to 22 solar masses and is around 1,700 times larger than our source of warmth and life. But that's not all. On one hand, observations have shown that the stellar colossus is already ejecting huge amounts of gas and dust from its bloated hull. On the other hand, WG64 recently became the focus of the first-ever portrait of an extragalactic star. We now have another impressive close-up of a star, thanks to the team led by Kichi Onaka from André Bello University in Chile. Specifically, the researchers used the gravity instrument at the European Southern Observatory's Very Large Telescope in Chile to capture the magnified image of a dying star outside the Milky Way for the first time ever. The instrument used data in the near and mid-infrared range to create the image of a red hypergiant shrouded in a dense veil of dust, apparently in its final throes. But what does this actually mean in concrete terms? Are the experts expecting WHG64 to turn into a blazing supernova at any moment? Well, not quite, because in an astronomical context, the timescales are somewhat different. Although the researchers do indeed assume that the star will explode in the near future, the word near still covers a period of 1,000 to 10,000 years. For the universe, that's no more than the blink of an eye. But unfortunately, it's too long for us to be able to witness this spectacle in the sky. What we can witness right now, however, is that WHG64 is undergoing a series of drastic changes that pose a few puzzles for scientists. As the astronomers realized from the close-up, the surrounding cocoon of dust and gas has a very different shape than would have been expected from earlier observations and models. To be more precise, we are dealing here with a strangely egg-shaped cocoon, and the experts do not yet know how this strikingly elongated shape came about. WHG64 has dramatically lost mass. One possible explanation is based on the assumption that the red hypergiant expelled the material of its hull unevenly, perhaps during a particularly large outbreak. Alternatively, the asymmetrical shape could also be due to the influence of a companion star, even if this has yet to be discovered by the experts. And yet, egg-shaped cocoons were not the only surprising detail revealed by the close-up. The researchers also discovered that the star, quote, has undergone a significant change over the past 10 years. Specifically, the near-infrared radiation from WHG64 has increased significantly over the last 25 years or so, while at the same time remaining stable in the mid-infrared. According to scientists, this measurable change in the shape of the spectrum could be explained by the formation of hot dust in the immediate vicinity. In this respect, WG64 is reminiscent of a certain Betelgeuse, another gigantic star that has 800 times the diameter of the Sun, and is also in the last chapter of its life. The common feature of these departing giants is the fact that the ejected stellar material first condenses into transparent grains of aluminum oxide and magnesium silicates. Subsequently, iron-rich silicates are deposited on these grains, which absorb more radiation, causing the near-infrared radiation generated by the heated dust to increase, while the celestial body itself appears darker in visible light. Co-author Jaco van Loon from Kiel University in the UK says the hypergiant WG64 is one of the most extreme of its kind, and any drastic change can bring it closer to an explosive end. That said, drastic changes do not only affect the differences in infrared radiation. This becomes clear to us when we consider the enormous amounts of mass WG64 has already lost. New measurements show that the star is in the process of shrinking dramatically. To be more precise, it has already lost 10 to 40% of its mass, and now has only half its original radius. As we can see, everything points to WG64 rapidly approaching its end. Well, unless there is something to the companion star theory. In that case, its presence could have distorted the previous measurements, which means that the supernova could be a little longer in coming than currently suspected. In principle, however, the lifespan of such large stars is less than 40 million years, which makes them something of a stellar mayfly in a cosmic context. While our sun has already been around for 4.6 billion years, it will continue to burn like a normal star for another 6 billion years. But then, at some point, the time will come when its hydrogen supply in the center is exhausted, and it will swell into a red giant. This in turn will transform into a white dwarf. And so, as the last remaining part of the sun's shell, it will be shrouded for some time by a so-called planetary nebula. Why stars explode? There is no question that supernovae are among the most spectacular spectacles the cosmos has to offer. But what actually causes stars to explode at the end of their lives? And what factors influence this brutal finale in detail? Basically, the radiation pressure of a star is no longer sufficient to compensate for the enormous force of gravity due to decreasing nuclear fusion, and the core consequently collapses. This collapse goes hand in hand with a powerful explosion. The shockwave is so extreme that it hurls hot gases deep into space. The radiation released makes the supernova shine brightly for about 100 days. Once the hydrogen-rich stellar hull has been ejected, either a stellar black hole or a neutron star remains at the center. In the case of particularly massive stars, such as WHG 64 with more than 10 solar masses, experts speak of a Type 2P supernova. And although their progression is always the same, this type of supernova always has individual properties, for example in terms of its luminosity or the shape of the remnant. But what exactly are these differences? That is precisely the question the research team led by Kaiyan Yu from National Tsinghua University in Taiwan asked themselves. To answer it, the researchers used a computer model to simulate over 1,000 variants of the development and supernova of massive stars, and then compared the light curves generated with the observational data of real stellar explosions. The bottom line was that the appearance of the supernova explosion is directly linked to the properties of the star. The experts found, for example, that the metal content and rotational speed of massive stars have a significant influence on the subsequent supernova. More specifically, fast rotation affects the inner structures of the star and increases convective mixing and mass loss, which may affect the brightness and duration of the supernova. Furthermore, the luminosity and duration of the brightness are also likely to be influenced by the released energy and the amount of radioactive isotopes. While higher explosion energy goes hand in hand with a brighter but shorter supernova, a high amount of radioactive isotopes increases the duration of the brightness. And the reason it is so important for astronomers to understand the background of supernovae becomes clear when we remember. It is not just a breathtaking explosion that shows us the primal forces of the cosmos. No, because the elements ejected in a supernova also pave the way for the birth of new stars and planets, and thus, for the development of life.